Thank you very much for asking me to speak, and this is a very big turnout for a Sunday afternoon. I'm recognising some faces in the audience here. So yes, I just realised when you said who can have it that I've left off one slide, which was the one of who's eligible, so do remind me to say that if I forget. Okay, next slide. So Intrabeam is a type of accelerated partial breast irradiation. So the accelerated means giving it in a far shorter time frame, so accelerating the dose. Partial breast meaning to give it to part of the breast instead of the whole breast, because it's standard to have whole breast radiotherapy. So the type that we looked at, Intrabeam, gives a single dose at the time of surgery, because there are other ways you can give accelerated partial breast, and I'll touch on that soon. But it did represent the first form of tailoring in breast radiotherapy. So if you go back 3,500 years ago was when the first documented case of breast cancer was first in existence. It's in the Edwin Smith Papyrus in Egypt. And if you go then forward another 3,400 years, there was no change in breast cancer mortality or treatment over that time. All of the treatment gains have been in the last 115 years. And in fact, it was back to the 1900s when people actually for the first time started surviving breast cancer, but at a very big cost. The doses given for everything, for surgery, for radiation, for chemotherapy, were the maximum tolerable dose. So basically, what is the dose that a person will die from, and we'll just drop that back one notch. And so that's always been how we started giving breast cancer treatment. And it worked, but at a huge cost. And so particularly over the second half of the last century, there has been a big paradigm shift, moving from the maximum tolerable to the minimum effective treatment. And it's very hard as clinicians to give less treatment. But actually, breast cancer is not one disease. All of the women or men in the room who have had breast cancer, all of your diseases will be different, and we will have treated them all slightly differently. So it doesn't really make sense that we give everyone the same treatment. So over the last 100 years, we've improved on a lot of things. We've improved on breast screening. This was the first breast screening program. It was not very effective, but we've moved on from there. Next slide. The last 100 years, so we've gone from the Halsted's radical mastectomy, and there's a photo of what it looked like. What it doesn't show there is almost certainly the huge arm that she was going to develop as well. In the 1990s, the biggest reason for bone marrow transplant in the States was for breast cancer treatment. Now, we know that bone marrow transplant doesn't work for breast cancer treatment now. So that was how big the chemotherapy got at one time. We used to take out all the lymph nodes and more, bringing about huge rates of lymphedema, but not improving survival at all. We've got improved breast screening now. Our latest with 3D tomosynthesis is even better than the 2D digital mammography, which we thought was already excellent. But if you looked at that last 100 years, we were giving the same radiotherapy. In fact, it was about 15 years ago where they decided to add on one more week because a boost was better in high-risk patients as well. So we were giving 5 to 6 weeks of treatment to everybody. We know that some women are going to need a mastectomy, other women are going to need a lumpectomy or partial mastectomy. We know that we can do sentinel node biopsy in some women and take out all the lymph nodes in others. We know with small, low-volume disease, we can give you radiation to your axilla. So we're tailoring all of our other specialties, but we never were tailoring radiotherapy. Next slide. So if I go back to a little bit of the science, because this is about bringing research into reality, there are a couple of important studies that made us think about why we were giving radiation to the whole breast. This is an image diagrammatically of breasts in women who had a mastectomy for their breast cancer. And these are all of the other cancers seen in their breast on their mastectomy specimens which were not identified preoperatively, and we were also not treating. And you can look at mastectomy specimens too, and you can see that women, we all have a number of other cancers. We have other cancers in our body which our immune system is dealing with all the time, or that will never kill us and remain dormant. So we don't actually have to treat them all, because you're giving treatment with potentially life-threatening side effects for a disease that was never going to harm you. The other thing that happened, next slide, is the Milan 3 trial. And this Veronesi is a famous Italian surgeon who pushed for breast cancer conservation. In fact, when he turned up to the World Health Organization in 1955 to say, I want to do a trial to compare mastectomy versus partial mastectomy, he was ordered out of the meeting. So it was a big deal back then to give less treatment. But in his study where he was doing that, 273 patients then refused to have the radiation that followed. And they were followed up, of course, because they're all in the trial. And what they determined was that most of the recurrences were around where the cancer came out, which is indicated by the scar here. These were other cancers that turned up. So we call those elsewhere cancers. So not the same one, another one in the same breast, or in the other one. And it turns out that the elsewhere on the other side and the same side were about the same. So it meant that giving radiation to the whole breast wasn't stopping you getting other cancers in the rest of the breast. So why are we treating the whole breast? We never determined that the whole breast was the target organ. Next slide. When you give radiation, you also have a lot of organs at risk. So even with the newer technology, and there is an even newer technique now which tends to brush past, this is a CT scan. In medicine, we look up the body in our scanning. So that is the right side, this is the left side, these are the lungs here, vertebra at the back, sternum at the front, and this is the heart sitting slightly to the left side. So here's the breast, which as we know doesn't actually sit on the front of our chest when we lie down, it belongs in the underarm. So here it is, much to my 13-year-old's dismay. She said, what are they doing there? This radiation goes onto the front of, onto the lungs, front of the heart, the ribs. It can track round to the underarm as well, so it can influence lymphedema as well. And also, it can get the other breast. So in a large-breasted woman who would be sitting with her breast heaped up here, you can see that the rays coming through from the side to get that middle breast will also be hitting the other lung and the other breast. So you've got to know that you're giving it for the right benefit. And certainly radiation does have a survival benefit, so in the right people, you should be having it. Next slide. So a couple of questions. Are we over-treating by giving the same dose to everyone? But the other thing, is the whole breast really the target organ if we've just got the cancer in one place? Next slide. So this is where accelerated partial breast irradiation came in. You can give it over a shorter time and a targeted area. This is one type of it. This is an Intrabeam. This is me testing which probe I'm going to use because we have different sizes. But you can give it lots of different ways. You can use the standard linear accelerator, which a lot of women here will have had radiation in. You can have catheters put into the breast and have iridium seeds fed down, lots of different types. But the reason I wanted this type was back in 2005 when I went looking for this in Milan. I went looking for it at another technique actually and then saw this. This one can be done at the time of surgery. It's the cheapest way to deliver it and it's the least cumbersome for women with the least side effects. So that was the reason why I liked this one. Next slide. So this is the Intrabeam system. It is a big heavy arm, which this is about a tonne, but this bit here is the active radiation. It's only radioactive when it's turned on. So once you've had it, you are not radioactive at all, and the device isn't either. But that weighs about 2.5 kilos and is transportable in a suitcase between sites. So it's possible to have these arms, these sets of probes, and your console sited in different hospitals, and actually they can share the head because that's their $1 million bit. The rest is just the extras. It delivers quite a different radiation because a lot of you will be thinking, how can you get one dose and compare that to 15 to 25? It's a totally different radiation. So if this room is a cell, standard radiation that you go into a bunker is really, really high energy or high velocity. So an electron, which is what's going to cause the damage, will fly through that wall and it will go straight out the other side. And its target is your DNA and water molecules. So radiation will hit DNA and it needs to damage both strands of it to cause a lethal enough injury to get the cancer cell to die. The other thing it does is it hits water molecules, and from that you produce oxidants. So you'll hear of antioxidants that you take. Well, oxidants is your immune system way of causing damage and destroying cells. So with having one electron fire through, that is unlikely to kill the cell. The cell will probably repair its one strand of DNA in about 2 minutes. But if you give too much dose, it will damage all the other tissues. So that's why you go 15 to 25 times, and you have to keep hitting the same cells again and again to get that cell to die. With low energy radiation, which we deliver here, we do it in a standard operating room that hasn't been modified. It's very low energy. So basically, the electron will come into the cell and it will bounce off and ricochet off the walls. It won't have enough energy to get through too many more cells. So it has really high cellular damage. It destroys the inside of the cells, but it doesn't go very far. So it means that we actually have what we call a higher tumour cell kill. So this dose of 20 gray, so gray is a measure of radiation that we use, we give 20 gray in 20 to 30 minutes to this area. It will only treat 1 to 2 centimetres, and then by then the dose is gone. But the tumour cell death rate is extremely high in that area, and it's the same as giving 60 to 70 gray on a daily dose. Your treatment in a linear accelerator is 40 to 50 gray over that 15 to 25 weeks. So you can see that by equivalent treatment, it's a much higher dose, but it doesn't cause the damage. You don't know you've had it. You don't get a burn. You get a little bit more seroma fluid in the wound, but you don't really know that you've had the radiation therapy. Next slide. So this is what it looks like when it's already attached to the machine. Our anaesthetist stays in the operating theatre behind a lead glass window so that they can monitor you, and we can stop the treatment during surgery if we need to. And it's about 20 to 40 minutes depending. Next slide. So the TARGIT A trial was the main trial that studied this, and it's actually one of the biggest radiation trials ever done in breast cancer. It was done in 33 centres in 11 countries worldwide, including Australia. The actual device was designed for brain tumours back in 1995, and it was first used in breast in 1998. So this treatment is nearly 20 years old. 20,000 women around the world have had this treatment already. Next slide. And next one again. So what happened with the TARGIT trial? 1,700 women got randomised to the TARGIT treatment, the single dose, and the other group were assigned to standard. So that stands for external beam radiotherapy. So that's the standard treatment. And the trial took place over 12 years. It started in 2000. Next slide. You could get the treatment at the time of surgery. So that's how we do it in New Zealand. We take the tumour out, we check your sentinel node. If it's all right, we will give you the radiation. The other type was another question which is really important for countries that have a lot of distance to travel, like Australia, for instance, or even New Zealand, really. You did your surgery first, worked out if they were suitable, and then brought them back for a short, sort of 30 to 40-minute operation where the patient would go to sleep and you'd deliver it. And that's called a delayed procedure. Next slide. It was a risk-adapted design. So what that meant is that it had to apply to the real world. If we did your surgery and it turned out that we'd given you radiation and your tumour was worse than the criteria we wanted to do, we were allowed to give you external beam radiation as well. And that in the study, 15% were allowed to do it. In mine and Maria's hands in New Zealand, 9% of our women will go on and have external beam radiation afterwards. Whilst that's very disappointing, the women who get that get the second lot of radiation would have 5 days added onto their radiation normally anyway because of that, because of those high-risk features. So in fact, that single dose has replaced that 5 days at the end. Next slide. So these were the results. I'm only showing the pre-pathology, which meant giving it at the same time because the post-pathology didn't work as well. There's something very key about giving the radiation as soon as you've removed the tumour. So in the control arm, there's a 98.9% versus a 97.9%. So that's a non-significant. You can have the local recurrence rates within 2.5%, and then that was deemed equivalent. In fact, what we know from breast cancer is they could be 10% apart before you affect mortality. So most of the time, cancers recur in the breast. It doesn't cause a change to people's survival. Next slide. Breast cancer mortality, again, 3.3 versus 2.7, so that's a non-significant again, so that's considered breast cancer survival's equivalent. Next slide. But this is the significant bit, non-breast cancer deaths. We know that radiotherapy can cause cardiac death and second cancers. The reason we use it is because we know that the risk of breast cancer mortality is higher and that breast cancer radiation can improve survival. But if you are giving it to a group of women who have low-grade early breast cancer who will not die from their breast cancer, then it's unacceptable to give them a treatment-related death. And the eligible patients for the TARGIT trial are less than 3 centimetre, grade 1 or grade 2 ductal cancers that are hormone receptor positive and not in a lymph node. So a classic screen-detected patient, and we have an excellent breast screening program in the country, so that's why we have a number of women that can have it. So a third of breast cancer patients can have it, which equates to 1,000 women a year in New Zealand. So here we have a statistically significant amount, now 4.4 versus 1.3%. Next slide, which meant that the overall mortality favoured a single dose treatment compared to a whole breast radiation treatment. Next slide. Complications, again, fewer in the TARGIT treatment than whole breast radiation, and in fact, people wanted it. The interesting study on the patient preference shows that women make decisions quite differently than doctors will often predict. Women will make decisions based around access, children, travel, jobs. So we know in New Zealand that women who live more than 30 kilometres away from a radiation centre will have a mastectomy for a small cancer rather than travelling for 3 to 5 weeks of daily radiation. Particularly Kiwi women, we're very practical like that. But that's also unfair to do a mastectomy for a 1 centimetre tumour because people can't have access. Next slide. So, 2 things happened to me, and this drove me bringing this in. We have a huge inequality in breast cancer treatment. Rural women, Maori and Pacifica women, are 50% more likely to have a mastectomy than the same European woman having a breast-conserving surgery. They are less likely to have radiotherapy, which puts people at risk of local recurrence and potentially death if you're a high-risk patient. And they're also less likely to have access to breast reconstruction. So 44% for European versus 11%, totally unacceptable in this health system. So one of the issues here is that this addresses an access issue as well. Next slide. The other thing is, and this is a screenshot from a Sunday program last year, Carolyn, one of my dear patients who's since passed away, and I smile when I think of her because she was such a character. She told me in no uncertain terms when she was dying that I had to just do better and try harder and that it wasn't good enough. And so here I am. In 2011, I decided that the data was mature enough now to bring it in. Next slide. And so in 2013, I created Focus Radiotherapy. So it took 2 years before Maria Pearce, who's my radiation oncologist, and I could introduce this to New Zealand. It is about $5,000 to $8,000 per patient less between the public and private system. We give 1 dose at one time, and it's safe and effective. Next slide. I created World War III. I had no idea. I was naive Erica from Palmerston North, and it never occurred to me what a problem with this would be, and it's been huge. So it's been 4 years now since we've had it in, and the professional and personal toll has been quite huge on Maria and myself. It turns out that it's too disruptive. So if you're invested in standard linear accelerated treatment, you don't want 1/3 of your patients to go off a LINAC. You get paid less to provide one treatment. And also, to be fair, a number of my colleagues, I am early to innovate. So whenever you look at innovation of any new technology outside medicine as well, there's always the early adopters. There's the people that sit in the middle, and then there are the laggards. So I am an early adopter, and I admit that. But we are well and truly in this mid-range now, and we should be bringing it in. So that's the other issue. Sorry, I'll speed up. So it has been quite a big deal bringing it in. Next slide. It is my attempt to address some of the inequalities we've got. There will be greater accessibility. You could supply New Zealand with 2 mobile heads and 7 arms, and people would be able to get access, because whilst women can't travel for 4 to 6 weeks, they can travel for 2 or 3 days. So we can do that. You could put this on an operating bus and drive it around the country if you wanted to. It's cost effective, so the treatment alone is cheaper. Breast cancer costs patients employment, childcare, living away, and if we're doing less breast reconstruction, which is expensive, then that also saves money. We can share equipment between DHBs. We can use this in other cancer types. So breast is not the only one. You can use it in colorectal, neurosurgical, head and neck. And there's a less burden on current radiation technology for which we are currently under-commissioned for our population and cancer growth. Next slide. So where we are now, all insurers cover this except for Southern Cross. The National Health Committee, I got that onto the work list for them to assess it, and they're a group that advised the Cabinet and Ministry of Health on it. They found it to be safe and effective, and then that committee was disbanded under the national government. That Ministry of Health and then Minister denied the existence of this report and said that it was a draft only. My Official Information Act investigation has concluded that they were lying about that. So I'm looking forward now to my new Minister of Health. And it was, and whilst in opposition when I went to lobby in Parliament, it was supported by Labour and New Zealand First. So I'm hoping now I can continue to bring it in. I'm not commercially conflicted. I have no interest in supplying this to the public health system. It is very cheap and effective to do on their own, and I've provided them with all the IP. I've trained 20 clinicians for free. We will put, support, we'll let you pilot it, But long term, this is a really easy thing for the public health system to do. And I think we're just about there. And last slide. And this is the plaque on the machine, as Carolyn continues to remind me on a daily basis that I need to keep trying harder. Thank you.